Well, hello again. In this example, you will see how to apply the matrix-based stiffness approach to solve for typical structural responses in a truss. We will specifically be looking at this truss assembly, and we have already been given the global stiffness matrix for the entire structure. You'll also see that the degrees of freedom have appropriately been labeled, where these degrees of freedom are the unrestrained degrees of freedom, and these are those that have restraint. You'll also notice the applied load that we have here. Thus, let me go ahead and label the reactions the way we know them. And I also want to label the degrees of freedom as they show up on that stiffness matrix. So with the stiffness matrix in hand, our next step is going to be to develop and assemble the force vector, and then we will go ahead and partition it. So we will assemble this force vector according to the degrees of freedom that we have here. So we have actual forces applied at each of the degrees of freedom 1, 2, and 3. And then we have unknown reactions at degrees of freedom 4 and 5. So following the sign convention where acting to the right is positive, acting to the left is negative, we get negative 3.2, 6.0, 4.5. Then we have an unknown reaction R4, unknown reaction R5. Now what we want to do is we want to partition this vector according to the unrestrained degrees of freedom versus the restrained. So once again, the unrestrained degrees of freedom are degrees of freedom 1, 2, 3, and the restrained are degrees of freedom 4 and 5. The way we have traditionally labeled this is for the unrestrained degrees of freedom, we would call it F sub U, and for the restrained, we would call it F sub R. In a similar fashion, we need to partition the stiffness matrix according to the same degrees of freedom. So since 3 and 4 is the boundary between the restrained and unrestrained, we will partition according to this. Then let me go ahead and label these so that we are clear on what this is representing. This is what we would call KUU. This is what we would call KRU, KUR, and KRR. And as you are going to see, really the only ones that we are going to use in any calculations will be KUU and KRU. In fact, that is the next step that we need to do. We've got this basic matrix formulation that says the force is equal to the stiffness multiplied by the displacement. Notice how that is written all in terms of the unrestrained degrees of freedom. I can then rework that so that I can solve for my unknown displacements. Delta U, and that will be a column vector, is equal to KUU, but I'm going to have to take the inverse because what I'm essentially doing is I'm moving that to the other side. And so then I get this force vector F sub U. If I perform that matrix operation, then I can solve for delta U as being 0.0385 inches, 0.2720 inches, and 0.1900 inches. So what we already have now is we have the displacements of the 3 degrees of freedom 1, 2, and 3. I will then utilize that information to be able to find the reactions. And that will be found through this set of matrix operations. So F sub R representing forces at the reactions, KRU multiplied by delta U. We carry out those operations and we'll get negative 1.23 kips, negative 6.07 kips. I want you to note that the negatives on that indicate that we assumed the incorrect direction. Notice the directions we assumed. So that means that if I were to sketch this on my diagram now, I know that this reaction is 1.23 kips. This is 6.07 kips. So currently we have the joint displacements. We also have the reaction forces. The last thing we want to find are the member forces, and we'll do that the old-fashioned way, meaning we'll come in here, and if I want to know what the force is in member 1, I will make a cut in member 1, and I'll sketch that free body diagram here below. So N1, and we've got this known reaction here of 1.23 kips. And then I will go ahead and sum forces in the x direction, and that will reveal to me that N1 is equal to 1.23 kips. It would be positive, meaning that is tension. And in a like fashion, if I wanted to know what was happening in member 4, I would make a cut, sketch the free body diagram, and get the reaction on there. Sum of forces in the x then reveals that N4 is equal to negative 6.07 kips, which we know represents a compressive force. Then if I want to know what's happening in member 2, make a cut in member 2, free body diagram, and then of course sum forces in the x direction. That reveals that N2 is equal to 4.33 kips positive, meaning we are in tension. And lastly, we will make a cut in bar 3. Then we will sum forces in the x direction. That reveals that N3 is a negative 1.57 kips. We know the negative then tells us that that bar is going to be in compression. So we now have joint displacements, reactions, and also the internal forces in the truss members. That concludes this example. As always, it's a beautiful day for studying structures.